It sounds simple enough. Space and time. Two everyday words we think we understand. But in the 20th century, physics revealed that these two are not separate. They are one. Space-time is the fabric of reality. It's the stage upon which everything in the universe plays out, from drifting dust to colliding galaxies. And it's not just a metaphor. It has structure, geometry, and as Einstein showed, it can bend. Before Einstein, time was thought of as absolute, a universal clock ticking the same for everyone. Space, too, was simply the emptiness in which things happened. But in 1905, with special relativity, Einstein showed that time is not fixed. It can stretch and compress depending on how fast you're moving, and space can do the same. Then, in 1915, with general relativity, Einstein went further. He proposed that mass and energy curve space-time, and that curvature is what we perceive as gravity. Imagine placing a bowling ball on a trampoline. The fabric dips under its weight. Now roll a marble across the surface. It curves around the dip, not because it's pulled, but because the fabric tells it how to move. That's what gravity is in Einstein's view, the geometry of space-time itself, directing the motion of planets, stars, even light. But this fabric is not made of threads or particles. It's a set of relationships between locations and moments described by mathematical rules. It stretches, it flexes, it evolves. When massive objects accelerate, say when black holes collide, they send ripples through space-time. We call these gravitational waves. Understanding space-time changed physics forever. It blurred the line between what is and when it happens. Every second that passes, every step we take, is woven into a larger whole. You don't move through space. You move through space-time, a four-dimensional landscape where past, present, and future are connected. And while we live within this fabric, we're still learning its shape, its texture, and its secrets. In 1915, Albert Einstein did something extraordinary. He rewrote our understanding of gravity, not as a force pulling objects together, but as the result of how mass and energy bend the geometry of space-time. That's the heart of general relativity. To grasp it, start with a simple question. Why does the Earth orbit the Sun? For centuries, we thought it was because of a gravitational force, an invisible pull between two massive objects. But Einstein offered a different picture. In his view, the Sun curves the space-time around it, and Earth isn't being pulled, It's moving along the straightest possible path in this curved geometry, like a marble rolling along a dimpled sheet. Earth simply follows the contours of the space-time landscape. This idea was radical because it meant that space and time aren't just passive backdrops. They are dynamic, shaped by what's in them, and in turn shaping how everything moves. To express this, Einstein created a set of equations, the Einstein field equations. They're complex, but they boil down to this: mass tells space-time how to curve, and space-time tells matter how to move. One of the first tests of the theory came in 1919 during a total solar eclipse. Astronomers measured the position of stars near the sun and found that their light had bent as it passed by. Einstein's predictions were correct. That bending of light, called gravitational lensing, has become one of the most powerful tools in modern astronomy. We've used it to find dark matter, measure cosmic expansion, and peer deep into the early universe. General relativity also predicted the existence of black holes, regions where space-time curves so steeply that not even light can escape. And it laid the groundwork for our understanding of cosmic evolution from the Big Bang to today. Despite its age, general relativity remains one of the most accurate theories in science. Time and again, it has been tested in GPS satellites, in the orbits of Mercury, in the detection of gravitational waves. It's a theory that didn't just change physics, it changed how we see reality, not as a static arena, but as a living, warping fabric in motion with the universe itself. We tend to think of time as steady, a constant rhythm ticking forward for everyone. But Einstein showed that time is not absolute. It can slow down or speed up, depending on where you are and how fast you're moving. This effect is called time dilation, and one of the most surprising causes of it is gravity. According to general relativity, the stronger the gravitational field you're in, the more space-time curves, and the more time slows down. This is called gravitational time dilation. It's not just theory. It's been measured with atomic clocks placed on mountaintops and in orbit. The results are clear. Clocks closer to Earth's surface tick more slowly than those farther away. So yes, if you live at sea level, you age ever so slightly slower than someone living in the mountains. The effect is tiny on Earth, just billionths of a second per year. But in stronger gravitational fields, like near a neutron star or black hole, time slows dramatically. Near the event horizon of a black hole, it can nearly stop. Even in our daily technology, time dilation matters. GPS satellites, which orbit Earth at high altitudes and speeds, experience both gravitational and velocity-based time dilation. Their onboard clocks tick faster than ground clocks, and without correction, GPS location data would become inaccurate by kilometers every day. Imagine this: an astronaut orbiting Earth for 6 months ages a fraction of a second less than people on the surface. If they traveled near a black hole or at near light speed, the difference would be much more extreme. This isn't science fiction, it's a built-in feature of reality. Time is elastic. It bends to gravity. And with every tick of every clock, the universe is reminding us where you are and what's around you shapes how fast time flows. In space, the clocks tell different stories, and some of those stories are slower than ours. Imagine this: 2 identical twins. One stays on Earth, the other boards a spaceship, accelerates to near the speed of light, travels for years, then returns. When they reunite, something astonishing happens. The twin who traveled is younger. This is the essence of the twin paradox, one of the strangest predictions of Einstein's theory of special relativity. But it's not really a paradox at all, just a consequence of how time behaves at high velocities. When an object approaches the speed of light, time for it slows down relative to an outside observer. This means that from Earth's point of view, the traveling twins' clock ticks slower, and when they come back, less time has passed for them than for their sibling. The effect is not symmetrical because the traveling twin changes frames, accelerating, turning around, and decelerating, while the earthbound twin does not. That switch makes all the difference. This isn't just thought experiment material. Particles called muons, created in Earth's upper atmosphere, decay rapidly. But when they move at near light speed toward the surface, they last longer than expected, because from their perspective, time slows down. We've observed this many times, so in principle, time travel to the future is possible. We can't do it yet on a human scale, but the laws of physics allow it. What about time travel to the past? That's a more difficult question. Some solutions to Einstein's equations, like closed time-like curves, suggest it might be possible under extreme conditions, near rotating black holes or using hypothetical structures like wormholes. But those ideas remain speculative. They often involve exotic matter, negative energy, or violate causality, the fundamental rule that causes precede effects. Still, the twin paradox reminds us that time is not fixed. It's relative, shaped by motion and gravity. And the faster you go, the less of it you experience. In a universe where time is stretchable, one truth remains. The clock is not the same for everyone, and for some, the future comes faster. We've grown used to the idea that mass bends space-time, but under certain conditions, mass doesn't just bend it, it twists it. This strange effect is called frame dragging, and it happens when a massive object spins. Imagine space-time as a pool of thick honey. Now drop a heavy spinning ball into it. Not only does the ball create a dip, it also causes the honey nearby to swirl around. That's what a rotating planet or star does to the space-time around it. It drags it along with its rotation. This idea was first predicted by Austrian physicists Joseph Lense and Hans Thirring in 1918, just a few years after Einstein published General Relativity. But it took nearly a century to prove it. In 2004, NASA launched Gravity Probe B, a satellite equipped with ultra-precise gyroscopes. It orbited Earth and measured how its rotation pulled on local space-time. After years of analysis, the results were clear. The gyroscopes had shifted ever so slightly, just as general relativity predicted. This means that near a rotating object, the very coordinate system of space and time is being twisted. And this isn't just an abstract curiosity. Near extreme objects, like neutron stars or spinning black holes, frame dragging becomes incredibly strong. A region called the ergosphere forms around a rotating black hole where nothing can remain still. Even light is forced to co-rotate with the black hole's spin. This twisted space-time could, in theory, be harnessed. Some physicists have proposed using the rotational energy of black holes as a cosmic battery, drawing energy from the ergosphere using clever physics. Frame dragging also plays a role in pulsar timing, accretion disk behavior, and even the dynamics of gravitational waves. It's a reminder that space-time isn't a flat stage. It flows, it turns, and where mass spins, the very fabric of the universe spins with it. In the silent void of space, a new kind of signal is traveling. It's not light, it's not sound, it's the vibrations of space-time itself. These are gravitational waves, ripples in the fabric of the universe, caused by the acceleration of massive objects. Einstein predicted them in 1916 as a consequence of his general theory of relativity, but he doubted we would ever detect them. They seemed too faint, too subtle, too far beyond human reach. For a century, they remained a theoretical whisper. Then, in 2015, The whisper became a roar. Scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a fleeting signal. Two black holes, each dozens of times more massive than our sun, had spiraled into each other over 1 billion years ago. The collision sent shock waves through the cosmos, and when those ripples reached Earth, they stretched and squeezed space by less than the width of a proton. But LIGO was sensitive enough to see it. Since then, dozens of gravitational wave events have been recorded: black hole mergers, neutron star collisions, cosmic cataclysms unfolding in total darkness. Some of these events produce light, others don't. Gravitational waves let us hear what telescopes cannot see. And this new kind of astronomy is just beginning. Unlike light, gravitational waves are unblocked by dust or gas. They pass through everything. They let us peer into regions hidden from traditional telescopes, the hearts of supernovae, the cores of merging galaxies, the first seconds after the Big Bang. Soon, new detectors, like LISA, a space-based gravitational observatory, will open even wider windows into the universe. We used to think of the cosmos as silent, but now we know. It rings like a bell, with each massive collision sending echoes across eternity. And when we listen, really listen, we don't just observe the universe, we feel its movements, not through sight, but through the trembling of space itself. When we look into the night sky, we see galaxies, hundreds of billions of them, scattered across the vast darkness. But those galaxies aren't just sitting still. They're moving away from us, and not because they're traveling through space, but because space itself is expanding. This idea, the expanding universe, is one of the most profound discoveries of modern cosmology. It began with the work of Edwin Hubble in the 1920s. He noticed that distant galaxies had light that was redshifted, stretched toward longer wavelengths. The farther away a galaxy was, the more its light was redshifted. The conclusion: the universe is growing. But what does that really mean? Here's where the balloon analogy comes in. Imagine a balloon with tiny dots drawn on its surface. As you blow it up, the surface stretches. And as it stretches, each dot moves away from the others, not because the dots are moving themselves, but because the surface they rest on is expanding. Now think of the universe as that balloon, only in 3 dimensions. Galaxies aren't flying through pre-existing space. They're being carried apart as space itself stretches. This expansion happens everywhere, not just at the edges. In fact, there are no edges, just more space unfolding. And this insight leads to something even more surprising. If the universe is expanding now, then in the past, it must have been smaller and denser and hotter. This is the foundation of the Big Bang Theory. But the expansion isn't slowing down, it's speeding up. Thanks to a mysterious force called dark energy, space is stretching faster and faster over time. In the far future, galaxies beyond our local group will drift so far away that their light will no longer reach us. The night sky will grow darker. Cosmic history will fade from view. The balloon keeps inflating, and we, on one small dot, are watching the surface grow. The Big Bang tells us that the universe began from an incredibly hot, dense state. But there's a twist to that story, a brief moment far earlier than what we usually picture, when the universe expanded faster than the speed of light. This is called cosmic inflation. It happened in the tiniest fraction of a second after the Big Bang, around 10 to the negative 36 power seconds. During this blink of time, the universe doubled in size again and again, ballooning outward at an astonishing rate. Not because matter was flying through space at impossible speeds, but because space itself was expanding faster than light. That sounds like it breaks the rules, doesn't it? But it doesn't. Einstein's theory says nothing can travel through space faster than light, but space itself can expand at any speed. And during inflation, it did. Why do scientists believe this happened? Because inflation solves several cosmic puzzles. First, the horizon problem. Why is the universe so uniform, with the same temperature everywhere, even in regions that could never have exchanged light or energy? Inflation suggests those regions were once connected before being stretched far apart. Second, the flatness problem. Why does the universe seem so perfectly geometrically flat? Inflation smoothed out any early curvature, like a balloon surface stretching smooth as it grows. Third, inflation helps explain the seeds of structure. Tiny quantum fluctuations during inflation were magnified to cosmic scales, becoming the foundation for galaxies, stars, and clusters. Though inflation is still a theory, it matches observations remarkably well, especially the cosmic microwave background, a faint afterglow from the early universe. We may never directly see inflation. It happened too fast, too early, too far beyond light's reach. But its fingerprints are etched across the sky. A moment when the universe, barely born, took a breath so vast that everything we know came rushing into existence, at a speed no particle could match, but space itself could. When we gaze into the night sky, we're not just looking across space, we're looking back in time. The farther away something is, the older the light we see. And with powerful telescopes, we can now observe galaxies whose light has been traveling for over 13 billion years. But there's a limit to how far we can see, not because the universe has an edge, but because light itself has a limit, the speed at which it travels. This limit defines what we call the observable universe, a sphere centered on us, stretching about 46 billion light years in every direction. Wait, 46 billion? How is that possible if the universe is only 13.8 billion years old? Because while light was making its way to us, space itself was expanding. So the objects that emitted that ancient light are now much farther away than they were when the light first left them. What lies beyond the observable universe? Most scientists believe the cosmos continues far past what we can seize, perhaps infinitely far. But beyond that edge, light hasn't had time to reach us yet. It's not a boundary in space, but invisibility. And here's something even more humbling. As the universe expands faster and faster, distant galaxies are receding at ever-increasing speeds. Some are already moving away from us faster than light, not by motion, but by the stretching of space. Their light will never reach us. They are permanently beyond our cosmic horizon. In time, more and more galaxies will cross that line. The observable universe will shrink, not in size, but in content. Eventually, we may find ourselves in a lonely sky, with only a few nearby galaxies still in view. So when we look at the deep field images from telescopes like James Webb, we're seeing not just the ancient universe, we're seeing the most distant pages of a story we'll never fully finish. A silent horizon surrounds us, beyond which the light has not and may never arrive. Time feels like the most basic thing there is. It flows, it ticks, it separates the past from the future. We wake, we sleep, we age, and time moves forward. But what if time isn't real? Not in the way we think. In physics, time is surprisingly slippery. In Einstein's universe, time is just one coordinate in the fabric of space-time. Not absolute, but relative. It bends near gravity, stretches at high speed, and passes differently depending on where you are. That alone is unsettling. But some physicists now go even further, suggesting that time may not be fundamental at all. Instead, it may be emergent, a feature that appears when many particles interact, like temperature emerging from the motion of atoms. At the deepest level, in quantum gravity or string theory, time may not exist in any meaningful way. Some equations describing the universe don't even include time as a variable. The famous Wheeler-DeWitt equation, a candidate for describing quantum space-time, is timeless. It describes a universe that simply is, not one that unfolds. This leads to strange questions. If the fundamental laws don't include time, why do we experience it so vividly? Why do we remember the past, but not the future? Why does entropy, disorder, increase? Some researchers believe entropy is the key. The flow of time may be a reflection of the universe's journey from order to chaos. We perceive time moving forward because we live in a universe where entropy increases. Others suggest that our experience of time is rooted in consciousness, in memory, in the way our brains track change. But if time isn't fundamental, what replaces it? Perhaps a landscape of possible configurations, a giant map where moments don't follow one another. They simply exist, side by side, like pages in a book, all already written. In such a view, the future doesn't happen. It is. And the past isn't gone. It still exists. Time, then, may be an illusion, but one we cannot live without. If you drop a glass and it shatters, you don't expect the shards to leap back together. A fire burns wood to ash, not the other way around. Milk mixes into coffee but never unmixes. These are all signs of one universal truth. Time has a direction. It moves forwards, but why? Physics is mostly time symmetric. The laws that govern atoms and gravity don't care whether time flows forward or backward. But in our everyday world, time clearly has an arrow. The reason lies in a single word: entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. A neatly stacked deck of cards has low entropy. A shuffled deck has high entropy. There are more messy states than ordered ones. In thermodynamics, systems naturally evolve toward higher entropy. That's the second law, and it's why time flows in one direction, because the universe is moving from order to chaos. At the beginning of the universe, entropy was incredibly low. The cosmos was hot and dense, but remarkably uniform. Since then, stars have formed and died, galaxies have collided, black holes have grown, and entropy has skyrocketed. The arrow of time, then, is a thermodynamic arrow. It points from the smooth past to the messy future. But this raises a deep mystery. Why did the universe begin in such a low entropy state? It's still one of the biggest questions in cosmology. If we rewound the universe, let entropy decrease, everything would move in reverse. We'd unbreathe air. We'd remember tomorrow instead of yesterday. But in our real experience, memories are linked to entropy. So are cause and effect. We act before results, not after. Entropy, then, doesn't just shape stars and galaxies. It shapes our sense of time itself. Without it, past and future would be meaningless. There would be no direction, only stillness. But with it, time marches on, one messy moment after another. Imagine standing near the edge of a black hole, not inside, but just above its event horizon. To you, time seems normal. Your heart beats, your thoughts unfold, your clock ticks, second by second. But to someone watching from far away, you appear frozen. This is gravitational time dilation at its most extreme. According to Einstein's theory of general relativity, the stronger the gravity, the slower time passes. And nothing warps gravity more than a black hole. At the edge of a black hole, the event horizon, space is so curved that light can't escape. And as you approach it, your time begins to stretch from an outside perspective. If you hovered just above the horizon, your seconds might become minutes to someone at a safe distance. Hover closer, and those minutes could become years. This isn't science fiction. It's been confirmed, not near black holes, but in more modest ways. Astronauts in orbit age slightly slower than people on Earth, thanks to both their speed and weaker gravity. On Earth, GPS satellites have to account for time dilation to stay accurate. If they didn't, your phone's location would quickly drift off course. But near a black hole, the effect is magnified. In the movie Interstellar, a team lands on a planet near a massive black hole. Because of its intense gravity, every hour on the surface equals 7 years back on their ship. The science behind that scene is surprisingly sound, a real extrapolation of Einstein's equations. This leads to haunting ideas. If you could survive close enough to a black hole, protected by technology we don't yet have, you might experience a few days, while centuries pass for the rest of the universe. Black holes don't just distort space, they pull on time itself, stretching it thin. So next time you imagine a clock ticking, picture it bending slowly under the immense weight of a collapsed star, because near a black hole the universe waits. And so do you. What if two distant places in the universe were connected, not by endless space between them, but by a tunnel? That's the idea behind a wormhole. It sounds like science fiction, and often is. But the concept has its roots in real physics, first proposed in 1935 by Albert Einstein and his colleague Nathan Rosen. They were working on general relativity when they discovered that under certain conditions, space-time could contain a kind of bridge, a shortcut between two regions. They called it an Einstein-Rosen bridge. Today, we call it a wormhole. Imagine space as a two-dimensional sheet. If you fold it and punch a hole through, you can move from one point to another instantly, skipping the vast distance in between. That's what a wormhole offers, a way to travel across the cosmos faster than light, not by exceeding the speed limit, but by taking a shorter route. But there's a catch, or several. First, wormholes are incredibly unstable. They tend to collapse before anything, even light, can pass through. To keep one open, you'd need something exotic, matter with negative energy density, the kind that might violate known physics. Second, even if a wormhole existed and stayed open, it might not be traversable by humans. Tidal forces near the throat could tear you apart. And third, there's the problem of causality. Some solutions suggest that wormholes could be used for time travel, allowing a traveler to emerge in the past. That raises all kinds of paradoxes, like the famous question, what happens if you go back and prevent your own birth? Still, wormholes remain a tantalizing possibility. They appear in the equations. They inspire movies and thought experiments. And in the quest for a unified theory of quantum gravity, some researchers believe wormholes may offer clues to how space and time are woven together. So far, no evidence of a wormhole has ever been found. But if one ever were, it could change not just our understanding of space, but of time, reality, and distance itself. We often imagine empty space as truly empty, a vast, silent void. But in the world of quantum physics, even nothing is something. Zoom in far enough, and what seems smooth becomes turbulent. At the smallest possible scale, the Planck length, space-time itself starts to froth and jitter. This is what physicist John Wheeler called quantum foam. Picture the surface of a calm ocean from a great distance, smooth and glassy. But up close, It's a storm of ripples, waves, and chaos. Quantum foam is like that, the fine-grained texture of the universe, too small for us to see, but not too small to matter. At this scale, a trillionth of a centimeter, the certainty of position and time breaks down. Particles pop in and out of existence. Energy fluctuates. Even the geometry of space itself may flicker, twisting, curling, maybe even briefly forming baby black holes or microscopic wormholes before collapsing again. It's like reality is boiling underneath our perception. This frothy understructure is believed to be the arena where quantum gravity rules, a realm where Einstein's smooth space-time and quantum mechanics finally meet. We don't yet have a theory that unifies them, but approaches like loop quantum gravity and string theory try to describe this granular fabric. Some suggest that space is quantized, made of discrete units like atoms of geometry. Others think that space and time may not even be fundamental, just emergent properties of deeper quantum relationships. But why does this matter? Because the nature of this foam may hold the key to understanding everything. Black holes, the origin of the universe, even the fate of information. The quantum foam might be the raw material from which space, time, and energy all arise. A seething chaos beneath the calm surface of reality. We can't see it yet, but its presence is whispered in equations, hinted at in experiments, and dreamed about in the minds of physicists. In the quiet fabric of nothing, everything may be waiting. When we gaze into the night sky, the universe feels endless. But is it truly infinite? And more importantly, what shape does it have? This isn't just a philosophical question, it's one of geometry, and the answer changes how we understand space, time, and the cosmos itself. There are three possibilities. The first is that the universe is flat. In this geometry, parallel lines never meet. Triangles add up to 180 degrees. It stretches on forever, in all directions. This is the universe that fits best with Einstein's general relativity and most modern measurements. Then there's a closed universe, like the surface of a sphere. If you travel far enough in one direction, you might return to where you started. There are no edges, but the total space is finite. It would imply a universe that could one day stop expanding and collapse in a big crunch. The third option is an open universe, saddle-shaped. Here, space curves away from itself. Parallel lines diverge. It still expands forever, but in a geometry that feels stretched and cold. So which is it? The answer lies in the cosmic microwave background, the faint glow left from the Big Bang. By studying its tiny fluctuations, scientists can measure the curvature of space, and what they've found is remarkable. The universe appears to be flat, to within a very small margin of error. Not perfectly flat, but so close that any curvature would have to exist far beyond the observable universe. This has deep implications. A flat universe supports the theory of cosmic inflation, a rapid expansion in the first fraction of a second after the Big Bang. It also hints that the cosmos might be infinite, or at least so large that we'll never see its edges. But geometry isn't the only mystery. Even in a flat universe, space can bend and twist locally due to gravity. Galaxies, black holes, and dark matter warp the nearby fabric, shaping everything from light to time itself. So while the global shape may be flat, the local landscape is anything but smooth. The universe may not be a sphere, or a saddle, or a loop. It may be a vast, expanding flatland, with endless room for stars, for time, and for questions. We often think of relativity as something abstract, a theory for black holes and distant galaxies. But it's not just the stuff of physics textbooks. It's in your pocket. Every time you use GPS to navigate traffic, find a coffee shop, or call a ride, you're relying on Einstein's ideas. Here's how. GPS satellites orbit the Earth at an altitude of about 20,000 kilometers. Each carries an atomic clock, accurate to a billionth of a second. These clocks constantly broadcast signals that your phone receives and uses to calculate your exact position. But there's a problem. Time doesn't flow the same everywhere. Because the satellites are high above Earth, they experience weaker gravity, which, according to general relativity, means their clocks tick faster than clocks on Earth. At the same time, the satellites are moving fast around the planet, and according to special relativity, that motion causes their clocks to tick slower compared to a stationary observer. The result? A mismatch. The gravitational effect makes the satellite clocks run about 45 microseconds faster per day, while their speed slows them down by about 7 microseconds. Combined, they gain 38 microseconds each day relative to clocks on the ground. That might sound tiny, but without correction, it would throw off GPS measurements by kilometers in just a day. So what do engineers do? They build relativity into the system. GPS satellites are pre-programmed to tick slightly slower, so that once in orbit, their time aligns with Earth's. It's one of the most practical proofs of relativity. Without Einstein's insights, your navigation apps wouldn't work. Your plane wouldn't fly the right route. Precision farming, disaster response, financial systems all rely on this subtle synchronization. So the next time you get directions, remember, you're not just using technology. You're using a theory forged in 1905, proven in 1915, and orbiting the Earth today. Relativity isn't just real, it's essential. Imagine a mass greater than our sun, crushed into a sphere just 20 kilometers wide. That's a neutron star. It's one of the strangest objects in the universe, and what happens inside it defies our everyday understanding of matter, pressure, and time. A neutron star is born in death. When a massive star runs out of fuel, it can no longer resist the inward pull of gravity. Its core collapses, and if it's not quite massive enough to become a black hole, it compresses into something else, a ball of pure nuclear matter. The gravity is so intense that electrons are forced into protons, creating neutrons, hence the name. The result? A city-sized object with a density so extreme that just a teaspoon of neutron star material would weigh 1 billion tons. But what's really inside? We don't fully know. The outer crust is made of iron and super-dense atomic nuclei. Deeper in, atoms no longer exist as we know them. Only a sea of neutrons, packed tighter than anything found on Earth. Some theories suggest that at even deeper levels, the neutrons break apart into quarks, the fundamental building blocks of matter. If so, the core could contain quark matter, or even a form of exotic strange matter, denser than anything else in the known universe. And then there's the magnetic field. Neutron stars often spin rapidly, sometimes hundreds of times per second, and some emit beams of radiation that sweep across space like a cosmic lighthouse. We call these pulsars. Their magnetic fields can be 1 trillion times stronger than Earth's. They can bend particles, warp light, and tear atoms apart. The surface, it's just a few centimeters thick. But the gravity is so strong that a fall from 1 meter would hit you at thousands of kilometers per hour. Time itself slows down near such gravity. Even though it's not a black hole, a neutron star's mass bends space-time profoundly. So what happens inside a neutron star? It's one of the biggest mysteries in physics, a natural laboratory of forces we can't yet replicate, holding answers about matter, energy, and perhaps even the origin of everything. In the quiet heart of a dead star, reality itself is rewritten. Time feels like it flows in one direction. Moments pass, memories form, and the future stays just out of reach. But is that direction forward, built into the universe? Or could time, under the right conditions, actually run backward? Let's start with the physics. The fundamental laws of nature, the ones governing motion, electricity, gravity, and quantum particles, are mostly time symmetric. That means if you filmed the universe and played it in reverse, the equations wouldn't complain. They'd still hold true. But in our daily lives, time feels very different. Eggs don't unscramble. Smoke doesn't return to a fire. Memories don't form from the future. This one-way flow is called the arrow of time. Where does it come from? The answer lies in entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time. It's why hot coffee cools down, but never heats back up on its own. Why things break, but don't unbreak. This statistical rule gives time its direction. But here's the strange part. Nothing in the fundamental laws requires low entropy in the past. So why did the universe start in such an ordered state? No one knows for sure. Some physicists believe that the arrow of time is not fundamental, that it emerges from boundary conditions like the smooth, low entropy state of the Big Bang. Others suggest that if you zoomed out far enough, time might look like a loop or even run differently in other parts of the cosmos. In quantum mechanics, things get even weirder. Some interpretations suggest time doesn't flow at all, that it's just a way for us to describe correlations between events. And yet, we feel it. We age. We remember. We act in the present, not the past. Could time reverse? Mathematically, yes. Physically, maybe, under extreme or hypothetical conditions. But for now, in this part of the universe, time still moves forward, 1 second at a time. Even if the equations don't care, we do. Nikola Tesla is remembered as one of the most brilliant inventors of the modern era, a pioneer of electricity, radio, and wireless communication. But beyond his concrete achievements, Tesla also had deeply unconventional ideas about time, energy, and the universe itself. In his later years, Tesla began to speak and write about vibrations and frequencies as the keys to understanding all reality. He once said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." To Tesla, time was not a simple ticking clock. He viewed it more like a dimension of resonance, a field shaped by invisible forces. He believed that just as we could tune into specific frequencies in sound or light, perhaps one could tune into different moments and times, or even redirect its flow. Tesla also speculated that all matter was composed of subtle vibrations. In his vision, every object, even every thought, had a frequency, and in a universe of perfect resonance, time might not be a river flowing one way, but a pattern that could be reshaped. These ideas often brought him into conflict with the mainstream physics of his day. While Einstein was formalizing space-time and relativity, Tesla was exploring ether, scalar energy, and nonlinear time, using the language of intuition and electrical engineering more than formal equations. Some of Tesla's most speculative work involved machines that could transmit energy through space. Devices he claimed could alter weather, heal the body, or even disrupt time. None of these were ever proven, but his notes, interviews, and unpublished patents have fueled decades of fascination and conspiracy theories. Did Tesla really understand something others missed? Or was he simply dreaming beyond the limits of science? Today, physicists study gravitational waves, quantum fields, and the fabric of space-time. They use tools Tesla could never have imagined, but chase questions he once asked. And while many of his views on time remain outside accepted science, Tesla's core insight that the universe is alive with frequency and energy echoes through modern physics, from string theory to quantum mechanics. He may not have built a time machine, but in many ways, Tesla was always thinking ahead of his time. Every story has an ending, even the universe. But how does time itself end? Cosmologists have proposed several possibilities, and two of the most compelling are the heat death and the Big Crunch. Each tells a different story about the ultimate fate of time, space, and everything we know. Let's begin with the heat death. This is not an explosion, but a slow fading. In this scenario, the universe keeps expanding forever. Galaxies drift apart, stars burn out, and black holes slowly evaporate. Over trillions of years, all motion winds down. Why? Because of entropy. As energy spreads out and systems reach equilibrium, there's less and less free energy to do work. Eventually, all temperature differences vanish. No more stars, no more life, no more change. The universe becomes cold, dark, and quiet. A sea of particles drifting through nearly empty space. Time, in a sense, loses its meaning because nothing happens anymore. That's heat death. A final whisper, not a bang. But there's another possibility, the Big Crunch. If the universe contains enough matter, gravity could one day overcome expansion. Galaxies would stop drifting apart and begin falling back together. Space would contract. Temperatures would rise. Eventually, all matter and energy could collapse into a single point, a mirror of the Big Bang in reverse. Time might run backward near the end, or it might end entirely, crushed under infinite density. Some theories even suggest the Big Crunch could trigger a new Big Bang, a cyclical universe, forever collapsing and rebirthing. But current observations show the universe's expansion is accelerating, driven by a mysterious force called dark energy. This makes the heat death more likely for now. Still, both endings force us to confront a haunting question. If time had a beginning, can it also have an end? And if everything stops, does that mean time itself ceases to exist? Or does the fabric of reality simply wait, quietly stretched, forever expanding into silence?